right, as we move into section 3.1, chapter 3, section 1, we're going to focus on functions. Now, the idea of a function is not a new concept. We did our parent functions in the last section, and we talked about transformations of functions. The function notation is f is a function of x. That's the same thing as y. And we've already used this function notation at least once. We're replacing y with the idea that y is the value of the function at some x, some input. Informally, a relation where each x value corresponds to only one y value is our function. Formally, a more mathematical definition, a relation is just any set of ordered pairs for which each element in the domain, because that's our set of x values, corresponds to only one element in the range, because that is the term for our set of y values. If you have a graph, it's easy to check to see something is a function by using the vertical line test. And hopefully you remember this from high school algebra. A relation is a function if a vertical line, any vertical line that you draw, only touches the graph in one place. So for every x value, if I do a vertical line through that x value, that vertical line is only going to intercept the graph in one location. Here is our example of our vertical line test. We've got a company's monthly revenue, all the money they bring in, and it asks what is the revenue when 36,000 phones are sold. Well, here's my vertical line through the revenue graph, and you can see that when 36,000 phones are sold, I have two different numbers for revenue. Well, does that make sense? No, absolutely not. I've got two different outputs, or y values, for one input, for one x value. And that's not functional. That doesn't make sense. Something is not right. You can only have one value that represents the amount of income. So that's not a function. Something has gone wrong. Okay, so these two graphs, we can apply our vertical line test to check to see if this relation is a function. This one, anywhere I would choose to draw a vertical line, it's only going to go through the graph in one place. So each x value has only one y value that corresponds to it. That's a function. For this graph, however, when I draw a vertical line, I can draw at least one vertical line where I intercept my graph more than one place. So this x value corresponds to two different y values, and that is not a function. That relation is not a function. Now, instead of a graph, now we have charts or tables of ordered pairs. So instead of our vertical line test, we're just going to use our definition that each element in the domain corresponds to only one element in the range. And as I go through my set of x values, my domain, I see that this 2 is repeated, and that 2 is repeated and corresponds to different y values, different values in the range. So that is not a function. What about this one? Well, each of my x values is different, which means it's going to correspond to only one y value, and that is functional. That works. On this last one, I see that I've got y values that are repeated. Is that a problem? Well, no, it's not, because the definition of function says that each x value corresponds to only one y value. It doesn't say anything about it being a problem for the y values to repeat. That is a function. An example of that would be our parabola. If we do, and this is just our parent quadratic function, f of x equals x squared, I see that my y values repeat. For example, if this is 4, that is going to be corresponding to where x is 2 and where x is negative 2, because 2 squared is 4 and negative 2 squared is also 4. Each of these x values only corresponds to one y value, but my y values are going to repeat. That is a function. Okay, finding the domain of a relation. Now notice it says a relation because every relation has a domain and a range, whether it's a function or not. Typically, if we have no restrictions, our domain is all real numbers. For example, our parabola, it extends forever in both directions. My domain here is all real numbers. And then I need to ask myself, do I have any values that make the function undefined? Is there a problem anywhere? For example, square root of a negative number is imaginary. That's not going to work as on my real number graph. Anything that causes me to divide by 0, that's going to be a problem because division by 0 is undefined. So let's go ahead and get those examples down here. First of all, we said a square root. If my function involves a square root, I'm interested in what is underneath that square root, and what is underneath that radical, the radicand, needs to be 0 or greater. So I have to think about this and set it over here and say whatever that is needs to be greater than or equal to 0, because negative values in the radicand, this argument under there, radicand, yields an imaginary number. So if I have a negative value, it's not greater than or equal to 0, it's going to give me an imaginary result. So that's a problem. My other problem, we said, was that if you have a variable in the denominator, we have to make sure the variable in denominator, I left out some letters there, denominator. Sorry, I get to talking faster than I can write sometimes. If I have a variable in the denominator, I have to make sure that I exclude from the domain, I kick out of the domain, anything that makes my denominator 0. Because division by 0 is undefined. Okay, let's look at the next page to get some examples of this. So we need to determine the domain of each of these relations, and then we're going to think about whether or not that relation is a function. First one here, we have a radical. Anytime I have a radical, what do we say? We need to make sure that what is underneath my radical comes out greater than or equal to 0, so that it's not going to be imaginary. So I have to say, okay, what would make sure that 5 minus x is greater than or equal to 0? That's what I'm looking for. Well, let's solve for x. If I subtract 5 from both sides, I have negative x greater than or equal to negative 5. I need to finish solving for x, which means that I'm going to need to divide both sides by a negative 1 to make that a positive x. And I just divided by a negative. When I divide by a negative, that inequality symbol switches. So I have x needs to be less than or equal to positive 5. These are going to be the values that make sure that I have a positive number or 0 in my radicand. So what does that look like on a number line? Well, my boundary value is 5, and I want values less than or equal to 5. So over here, up to and including 5. So my domain is going to be values from negative infinity up to and including 5. That's the domain of this function. And I can think about plugging some things in and making sure that I've got the right side. Something that's less than 5, 0 is less than 5. 5 minus 0 is 5. That works, that's real. If I plug in 5, 5 minus 5 is 0, and square root of 0 is 0, so that's okay. However, if I plugged in, let's say 7, 5 minus 7 is negative 2, imaginary value, that wouldn't work. Okay, Is this a function? Well, think about your parent functions. What's the shape of a square root? The parent function, square root x, is right there. Is that a function? Passes the vertical line test. So yes, it is a function. Okay, for the next one, y equals x to the fourth plus 3. I don't have a radical. I don't have a variable in the denominator. So we don't have to do a lot more with that. We can say, okay, that means that I'm good. My domain is going to be all real numbers. Think about this. If I plug in a number and raise it to the fourth power, is it going to give me a different value each time? Well, 1 to the fourth power, 1 times 1 times 1 times 1, that's just 1. 2 to the fourth power, 2 times 2 times 2 times 2, that's just going to give me one value. There's nothing in that that's going to cause me a problem. There's no plus or minus option. So this is going to be a function. In fact, this is going to look a lot like an x squared function. It's just going to be wider. Instead of a parabola, it's going to open up wider probably at the base. All right, oh, look over here. Remember we said to watch out for things that had variables in the denominator because division by 0 is undefined. So I need to look for things that are going to cause me to have 0 as my denominator. So I'm going to pull this out and I'm going to say what would make it equal to 0 because I need to exclude anything that makes that equal to 0. Solve for x, I'm going to add that 2 to both sides. I get x equals positive 2. If x is positive 2, I have a denominator of 0. That is where my function is undefined. So unlike this problem up here where we were saying, okay, this is going to give me my domain, for this one I'm saying, what do I need to kick out of my domain? So I need to exclude the value 2. Well, what does that look like as far as a number line goes? Well, I've got this 2, and this 2 cannot be in my domain, but I can use anything else. So my domain is 2 separate intervals here, from negative infinity up to 2, but not including, or from 2 to positive infinity. So I've written my domain in such a way that 2 is not included. Is this a function? Well, we haven't focused on the graphs of rational functions yet. That's what this would be. But this is a rational function. Anytime I have a variable in the denominator, I call it a rational function. Again, over here, we've got another rational function. We've got a variable in the denominator, so we know we're going to have to exclude something. So let's look to see what we need to exclude from this function. I'm going to take my denominator and I'm going to say, okay, we've got x squared minus 4 as my denominator. What causes that to be 0? Because I need to exclude anything that's going to cause my denominator to be 0. Now I can deal with this 2 different ways. I can either use my square root property to solve, or I can factor it. Now we'll look at solving that both ways. If I use my square root property to solve, I'm going to move that 4 over so that I have my squared term equals the constant. I add the 4 to both sides. And then my next step would be to take the square root. When I solve by taking the square root, I have to consider that this unknown, this x, could have been positive, it could have been negative, so I've got plus or minus square root 4. Square root 4 is 2. So when I solve using the square root property, I've got 2 possibilities, a positive 2 or a negative 2. Those are the values that I would need to exclude from my domain. The other option, the other way to solve this would be to say, okay, this is difference of squares. And difference of squares will factor. I can reverse FOIL that. Difference of squares will factor to give me conjugate pairs, x plus 2, x minus 2. Difference of squares. I'm taking the difference because I'm subtracting, and these are both perfect squares. So difference of squares factors out into conjugate pairs, 1 plus, 1 minus. The second term is the square root of whatever the constant was. And then I set each of those equal to 0. The zero factor property tells me that if I'm multiplying these two things together and the result is 0, that something times 0 is what gave me this 0. So one or both of these has to be equal to 0. And when I solve these equations, I get -2 and I get +2, which is the same thing I got over here. So these are the values that I need to exclude, because if I use those in my denominator, I get 0. 0 and the denominator is undefined. What does that look like on a number line? Because I need to write my domain statement. Well, I've got -2 and +2 that needs to be kicked out of my domain. So I'm not going to include those two values. I'll include everything else, and I can see that my domain, I'm going to have to write it with 3 different intervals. So I'm running out of space here. My domain is going to be from -infinity up to -2, or -2 to 2, or, and then finally 2 to +infinity, those 3 intervals. None of them, I'm not including the values -2 and 2. Okay, excellent. Function notation. I kind of ran my way down into this. Sorry. Function notation. F of x equals y. I started the notes talking about f of x equals y as our function notation. So you've already been introduced to that idea. This emphasizes that my function value is equal to the y value. The function value at some x is equal to that y value. Okay, so we are going to evaluate the given function for these values of x. This is my function, and I have 1, 2, 3, 4. I need to reset that. I'll try to get that done before you guys print that. I'm just plugging in whatever value I've given for x. So instead of f of x, I've got f of 1. That means I'm replacing x with 1. So 1 squared plus 3. 1 squared is just 1. That is 4. What about if I replace it with a -1? Well, that is a -1 that is being squared. So a negative times a negative is still a positive. That still gives me 4. Here I'm replacing x with a. So instead of x squared, I have a squared plus 3, and there's nothing else to do there. But here I'm replacing x with a plus 3. That a plus 3 is what's being squared. And then I want to add 3 to that. Now be very careful here. People tend to get in a hurry and they just say, oh, that's a squared plus 9 because I square it, I'm done. That's not right. You need to multiply a plus 3 times itself, a plus 3. You're going to get 3 terms here because we're going to FOIL. There's a shortcut you can memorize if you want to. You square the first term. You multiply the 2 terms together times 2 because the outside and inside products are the same when you FOIL, and then you square the second term. So you can walk through that shortcut in your head, or you can write it down and FOIL it out. If I FOIL it out, my first product, a times a, is a squared. My outside product is 3a, my inside product is 3a. That gives me a total of 6a, and then 3 times 3 is 9. And then I still have that plus 3 over here. So I need to combine like terms. And my result is a squared plus 6a. And then 9 and 3 is 12. Okay, very good. Don't forget that you're totally in control of these videos. Pause them, rewind them, slow me down. Whatever you need to do to get to understand what is going on. Okay. Application problem. The mean or average age of a woman in the United States when her first child is born can be approximated by this given function, x to this exponent. That exponent is 0.0565, where x equals 10 corresponds to the year 2010. So if x equals 10, that would be for the age of the woman who, when she has her first baby in 2010. If I plugged in 0, that would represent the year 2000. We want to estimate the mean or average age of a woman at the birth of her first child in each of these 3 years. Round your answer to 1 decimal place. So this is basically calculator math. but we got to throw in some order of operations. So for 2010, I'm doing x equals 10. My problem, f of 10, is 21 times 10 to the point 0.0565 power. So I'm multiplying 21 times this. Now, order of operations, parentheses and exponents first. I don't multiply 21 times 10. I raise 10 to my exponent, and then I multiply that result times 21. So when I plug that into my calculator, I need to say 10 to the power of, there's my exponent button, that little house top, 0.0565. That's first. And then I take that result and I multiply that times 21. Now we're told to round to 1 decimal place. That means that that woman would be about 23.9 years old to have her first baby in the year 2010. What about 2012? Well, for 2012, we're going to use 12 as our value for x, and then for 2014, we are going to use 14 as our value for x. We're focusing on the fact that the y, the result, is a function of the x value that we plug in using the formula that we were given. And paying attention to order of operations. Whoops, that should be 14, not 12. Order of operations, raise 12 to the power and then multiply by 21. You should get that in 2012, the average age for a woman when her first child is born is about 24.2 years old. And then finally in 2014, and I'll do this one on my calculator, I've got 14 to the power, 0.0565, and then I'm going to multiply that times 21. And I get about 24, we're rounding to the first decimal place, so 24.4 years old. Rounding matters. Make sure you round accurately. And then we ask, so what's happening? Is the average age of when the first child is born increasing or decreasing? Well, as I go from 2010, 2012, 2014, it's increasing. I see that slowly, not by a lot, but slowly, women are delaying when they get pregnant and have their first baby. Okay. Difference quotient. Now, when we talked about linear functions, we talked about slope, that rate of change. If you have a straight line, you have a consistent slope that is true for the entire function. But if you don't have a straight line, not a straight line, then we can still talk about an average rate of change, but it's not for the entire function. It's just between two given points. For example, if I look at this as my graph, well, right here, this is decreasing. This is negative. And then it turns and now it's positive. If I pick 2 points here, it's positive but kind of shallow. It's not very steep. If I pick 2 points here, it's still positive, super steep. So my difference quotient is going to give me a calculation that would allow me to have the average rate of change between any 2 points, no matter what 2 points I pick, anywhere on the function. Now you don't have to reproduce this. I'm going to tell you what the difference quotient calculation would be, and you just have to know how to use it. So if you pick an x value to start, so here's my x, and then you move over for the second point, h units, so that this next would be x plus h. My value, function value at this x is f of x. My function value at this one is f of x plus h, because that's how far I moved over. Those are the 2 points that I would be using to find the slope, right? Because you do change in y over change in x. Well, my change in y is the difference, f of x plus h minus f of x. And the change in x, the denominator, is that value, however many units I moved over, just h. So this is how I calculate the difference quotient for any function. We're going to show you mathematically what that looks like. Now, it is It's just making sure that you keep things straight, basically. It's just making sure that you keep things straight. So let's do this first one. This is a line. So what's my rate of change? Well, it's going to be the slope is going to be 3, right? That gives me a really good starting place to do an easy problem to make sure I know what I'm doing here. So I'm going to use f of x equals 3x plus 2. I want my result to be 3 because this was going to give me a straight line with a slope of 3. This is in slope-intercept form. And make sure I can get that mathematically using my difference quotient. My first step, I'm going to put everything over h. So let's just set it up with everything over h. And then my next step, in the numerator, I'm going to start with f of x plus h. So anywhere I have an x, I replace it with x plus h. So that would be 3 times x plus h plus 2. That's this first piece. And then the second piece says to subtract the original function. So I'm going to say minus, and then parentheses are important, subtract the original function. Now parentheses are important here because I have to make sure I distribute that negative. Alright, so all over h, this first part, I need to distribute the 3, multiply in the 3, 3x plus 3h, and then I have that plus 2. And then the second part of my numerator, that's like a negative 1 being distributed, so that becomes a negative 3x minus 2. And then I need to clean that up. So my denominator is h. In my numerator, I find that I have pairs, opposites add to 0. 3x and negative 3x add to 0. 2 and negative 2 add to 0. So what I'm left with is 3h over h. And anything over itself is just 1, right? So that's just 1. And my average rate of change, or my slope, because it's a line, is a constant. It's 3. Okay, this one's not a line. What is this? Well, this is my parabola. It's quadratic, it's a parabola, and my transformation is up 1 unit. So if I were going to graph this, I would go up with the vertex up to 1, and I've got my parabola. That's what this graph looks like. So when I calculate the difference quotient, I'm not going to get a constant because this average rate of change varies. Sometimes it's negative, sometimes it's positive, sometimes it's steep, sometimes it's not, depending on what points I would pick. So let's set up our difference quotient always over h. My first part of my difference quotient, I plug in x plus h anywhere I have an x. So I plug in x plus h and square it, plus 1. The next piece of my numerator, I subtract out the original function. So I subtract out, and then I put my function in parentheses, x squared plus 1. And then I start doing the arithmetic. So everything's over h. Here we go. We've got to square this binomial. It is not x squared plus h squared. It's going to give me 3 terms. So I'm going to say x plus h times x plus h. That's what this is. X times x is x squared. Outside product is hx. Inside product is hx. So I've got 2 of those, plus 2hx. Last product, h times h is h squared. And then I've got plus 1. Then the next part of my numerator, I need to distribute this negative inside the parentheses. So negative x squared minus 1. All right, and then I clean that up. I'm looking for opposites, pairs that add to 0. X squared and negative x squared add to 0. 1 and negative 1 add to 0. And I'm left with 2hx plus h squared over h. I need to finish cleaning this up. Now I've got 2 choices. I can factor the common factor out of these 2 terms, factor out an h, or I could split it apart. And sometimes this is an easier way to look at it. I've got 2hx over h plus h squared over h. And then I say, okay, well, this h, anything over itself is 1, so that leaves me with 2x. And then one of the h's is going to cancel here, so 2x plus h. And that is my difference quotient. This is how I would figure out the rate of change between any 2 points on that parabola. All right, we're going to do one more of these together. You know what? We are not. We're going to not do one more of these together. We're going to mark this. I'm going to encourage you to work on this, see what you can do with it, and then we can check it or we can go over it together in class. If you don't have class with me, you can do that with a tutor or contact me about doing it separately. So I'm going to make a note that we're going to look at that later. Okay, let's look at the next page. So we tried out the difference quotient, we got an introduction to it. Now we're going to talk about operations on functions. We are going to combine functions in different ways. First, we're going to just add, subtract, multiply, and divide. To find the sum, that's the answer to addition. Difference is answer to subtraction. Product is answer to a multiplication problem. Quotient is answer to a division problem. Now, if we are told to add two functions together, that's all we're doing. We're taking the two functions and adding them together in such a way that we combine like terms. Subtracting, same thing. Order matters with subtraction. Multiplication, multiply one function times the other. Division, one function becomes the numerator, the other function becomes the denominator. Now, for these values, I'm going to be working with some examples where I start with these two functions. What type of functions are these? That needs to be your first question anytime you see a function. Well, I see that these are both squared, so they're second degree. They're going to be parabolas. Quadratic functions, their graph would be a parabola. When I combine these functions, I am being told to combine them and plug in 1 for x. And it looks like, yep, I'm told to do that with each of these. So I've got some options here. My first option is going to be to find f plus g of x and then to plug in 1. Let's do it that way, and then we'll explore our second option. So if we do f plus g of x, and then we replace that x with 1, we would say f of x plus g of x. So f of x is this, 2x squared plus 3x plus 1, plus g of x, 3x squared minus 4. And then I'm going to combine those like terms. I'm going to say, okay, I've got two squared terms, so that would be 5x squares. I've got 3x, and then I've got plus 1 minus 4 gives me minus 3. So that's f plus g of x. What I'm actually asked to calculate is f plus g of 1. So I'll take that f plus g, I'll plug in 1. Anywhere I have an x. 1 squared is 1, that's 5. Plus 3 minus 3 gives me 5. So that's an option. Now if I do that way, I would have to start over with each of the separate functions in terms of x for each of these and go from there. My other way to do this, however, is to say, okay, well, since I'm interested in plugging in 1 for x for all of these, let's look to see what would f of 1 be. And what would g of 1 be? Well, here f of 1 would be 1 squared plus 3 times 1 plus 1. So 2 times 1 plus 3 plus 1 would be 6. And g of 1, 3 times 1 squared minus 4. G of 1 would be 3 minus 4 is a negative 1. So given this information, I can come over here and I can say, okay, well this would be f of 1 plus g of 1, right? Because we did f of x plus g of x, and then we replaced our x with 1. So I could just do f of 1 plus g of 1 if I know that f of 1 is 6, and g of 1 is negative 1, and 6 minus 1 is 5. That's what I got down here. So that allows me to come over here and say, okay, well, f of 1 times g of 1 would be 6 times negative 1, that's a negative 6. F of 1 minus g of 1 would be 6 minus negative 1. Well, that becomes 6 plus 1, which is 7. And then f divided by g of 1 would be f of 1 over g of 1. 6 over negative 1, that is just a negative 6. So you've got some ways to play with that operations on functions, combining functions, using your principal mathematical operations. All right, another application problem. A department store has 2 locations in a city. From 2008 to 2012, the profits for each of the store's 2 branches are modeled by these 2 functions. So this would be the model of profits for the first store. This would be the model of the profits for the second store. X represents the number of years after 2008. F and G represent the profit in millions of dollars. So we're not doing calculations. We're thinking about what these things mean. First question, what is the slope of f? So my first store, there's the function. This function is a linear function because it's just in terms of x, and it's in slope-intercept form. F of x equals y. F of x does equals y, but I didn't mean to write it down. mx plus b, slope-intercept form. So this is my slope. So for function f, my slope is a negative 0.44. What does that mean for the profits? Well, if my profits are moving in a negative direction, that means my profits are decreasing. So what I make next year is going to be less than what I make this year if my profits are decreasing. And then it asks about function g. So if I look over here, it's in slope-intercept form as well. It's linear. The slope of this line is going to be 0.51. Well, what does that mean about my profits? Well, it means my line is moving in a positive direction, so my profits are increasing. So in general, if I want to think about it, and I'm not doing values, but in general, if I graphed f of x, it has a negative slope, so my profits are going like that. And if I wanted to graph g of x, it has a positive slope, so my profits are doing like this. So now this store may still have profits, it's just that they are becoming less and less each year. The second store, the profits are growing each year. And this tells me, okay, find f plus g. So if I do f plus g of x, that's f of x plus g of x. I'm just adding the 2 functions together. So negative 0.044x plus 13.62. And I'm going to add the second function to that. And when I add those 2 together, negative 0.44 plus 0.51 gives me a positive slope here. And then I add these 2 together, and I see that combined profits, my baseline would be, my y-intercept, my baseline would be 25.02. So the slope of this function is positive 0.07, and I started to put an x there. Slope does not have an x. Slope is just a positive 0.07. So what does that mean? Well, that means that the second store is going to compensate for that first store. What they're gaining each year is going to compensate for what that first store is losing, so that overall, if I combine the budgets for both stores, profits are increasing slightly, right? The first store is kind of dead weight, it's dragging them down. But the second store right now is making up the difference. So what does this mean in business terms? Maybe construction is going on outside this first store. Major construction. It's really hard to get the store, and it's really impacted profits. So that's a short-term situation. So financially we're okay because overall we're still increasing our profits, and we can look forward to when that construction is going to be complete and this first store is going to recover. Okay. Last page of this section of notes. Composition of functions. We are still combining functions, but this is a different way. Composition of functions, our symbol is a little circle in between the 2. And with composition of functions, order matters. You have to pay attention to which function is listed first. F composite G is how I would read that. F composite G. of x. F composite g of x means that I'm taking my function g of x and I'm plugging it into the one that was listed first. I'm plugging it into my f of x function. So consider these given functions, f of x and g of x, and we are going to do the compositions that are given. All right, so let's work through these. First, we have f composite g of x, so I'm taking g of x as a function and I'm plugging it into f. So f is my outside function, g of x is getting plugged into that. Sometimes my color coding gets away from me. So my f of x function is the square root x. So I have square root of, and x is replaced with the other function, x squared plus 1. So that is what it is. There's no way to simplify that. So we're done there. Now let's go ahead and go down because this is f composite g of x. This is f composite g of 2. So I'm replacing the x with a 2. Now I can go straight here, and since I did f composite g of x, and I could say 2 squared is 4 plus 1, that's going to be square root 5. I could also go back and I could walk my way to that. Let me go ahead and write that down that we just did. We said, okay, that would be square root of 2 squared plus 1 is square root 5. I could also walk my way to that. I could start here, and I could say g of 2 would be 2 squared plus 1. That's 5. And then I take that and I plug it into my f function. My f function is square root x, so that becomes square root of that 5, and we're at the same spot. So if we didn't do this step first, we could do it in one step here. Not one step, but do it together there. All right, other order. G composite f of x. So I'm taking f of x, I'm plugging it into g. G is my big function. The f of x function is the one that's getting plugged in this time. So my g of x function says I'm squaring something and then adding 1. Well, what am I squaring? I'm squaring this other function. Now this can be simplified. The square root of x squared, the square root and square are inverse operations, cancel each other out, so I have x plus 1 as my result. Now for this one, again, I have an option of saying, oh look, I've got g composite f of x. If I want to do g composite f of 2, that would be 2 plus 1 or 3. But if I didn't start there and do that, I could start here and say f of 2 is square root 2. Square root 2, not square root x, sorry guys, square root 2. And then take that and plug it into my g function. So square root 2 squared plus 1. Square root and square cancel out, so that leaves me with 2 plus 1 is 3. And we get the same result either way. All right, application. Let's walk through this. You know what? Yeah, let's walk through this discount application. The regular price of a computer is X dollars, whatever the computer that we happen to pick is. F of X is X minus 400, G of X is 0.75X. Find F of 1,000. Well, F of 1,000, that's right here. So F of 1,000 would be 1,000 minus 400 would be $600. Did I take a $400 discount or a 25% discount if I do F of 1,000? If I subtract out $400, I am taking that $400 discount. And then it says find G of 1,000. So G of 1,000, my G function right there. There's my F function, here's my G function. I've got 0.75 times 1,000. That leaves me with $750. What am I doing there? Am I taking a $400 discount? No. Am I doing a 25% discount? Yeah, I'm taking 75% of the price. That means I took off 25%. So that's a 25% discount. Now it says to find F composite G of 1,000. So let's look through this composite function. I start with g of 1,000 and I plug it into the f function. Well, g of 1,000 was that $750. My f function says to take this and subtract $400, and that leaves me with $350. Well, what did I do first? I started with g of 1,000, and that was my 25% discount. So first, I did the 25% discount first, and then I subtracted the $400. That was my order here. Now we're going to do g composite f of 1,000. So I'm starting with f of 1,000. F of 1,000 was 600. And then I do g of 600. So g of 600 is 0.75 times that 600. I plug that into my calculator and I get $450. So for this one, I did the f of 1,000. I subtracted first. And then I took the 25% discount. Which order favors us if we are buying the computer? Well, if we are buying the computer, we want it to be cheaper, right? So if we're buying the computer, I want the discount first, because that's the biggest discount. That's the discount off of $1,000 instead of a discount off of $600. That's a bigger number. Which order favors the store? Well, the store wants you to pay as much as possible. So the store wants you to subtract first, because then when they take the discount is going to be a lesser value. Okay?